Hi class, in this lesson we are going to go through our fourth and final type of discrete probability distribution, the hypergeometric distribution. I think you'll find that this distribution is probably the most familiar with what you've already learned in chapter 3. Now, going back, let's look at previous probability distributions. In a previous lesson, we learned that the binomial distribution was something that modeled independent events, and we counted the number of successes. The hypergeometric distribution is quite a bit like the binomial distribution in that we are counting the number of successes. That is our random variable. The key difference here is that we are going to look at deep. Okay, now let's start off with a simple example. You should have already seen this when we covered chapter 3. You should have seen an example already like this. Now we have a lottery game where we select 5 numbers out of 20, and we have to match 4 out of 5 numbers to win the second prize. Okay, well, order doesn't matter in this case. What's the probability of winning the second prize? All right, now you guys should already be familiar by now that the probability of a second prize in this case is 5 choose 4 times 15 choose 1 all over 20 choose 5. All right, we've done quite a few questions like this already involving lottery games and how we can calculate the probabilities using combinations. All right, now let's try to generalize this into a formula. This type of example that we just did was an example of a hypergeometric probability. So the key difference between this and the binomial distribution is that we have dependent trials. Now let's break down the parameters. If we have X successful outcomes in R dependent trials, A is the number of successful outcomes available, and N is the population or number of possible successful outcomes, or number of possible outcomes in general, rather. Our formula, okay, let's look at the example of the lottery that we just did. How many successful outcomes were there? How many possible winning numbers were there? 5, right? And how many successful outcomes were we counting? We want to see what was the probability of getting second place, right? Which involved matching 4 of the 5 winning numbers. Okay? And N would be the total number of numbers available, right? There are 20 numbers. And lastly, R would be the number of trials that we did. We selected 5 numbers. Okay? So how can we generalize what we just did into a formula? We have A choose X times N minus A choose R minus X all over N choose R. Okay? Now think about it. We had 5 possible winning numbers. Okay? We wanted to see the probability of getting 4. Okay, and then we had to multiply that by the N minus A choose R minus X, right? The total number of numbers minus the number of winning numbers, which was 20 minus 5, which is 15, right? R minus X, how many trials minus the number of successful numbers, right? There were 5 trials, meaning we selected 5 numbers, and we wanted to get the probability of 4 of them matching. So 5 minus 4 was 1. And the denominator was just N choose R, right? Of 20 possible numbers, we chose 5 of them. Okay, so that is our formula for the hypergeometric probability. Okay, the expected value for hypergeometric distribution. Now, the expected value here is just a ratio of the number of available successes to the size of the population. What does that mean? That means it's just R times A all over N. Okay? So in this case, in our example, R was 5, right? We won, there are 5 trials and there are 5 possible winning numbers, and N was 20, right? There are 20 possible numbers to choose from. So this is 25 over 20, which is 1.25. And what does it mean in the context of that lottery? If we played that lottery many, many times, on average, we will match 1.25 numbers. Now again, the math for the expected value here is kind of complicated. We're not going to go through the proof for the formula. We're just going to learn to use the formula. Okay, so I kind of just went through the answer for B there, right? It was 1.25. Now let's look at another example of a hypergeometric distribution where we're going to complete a probability distribution, meaning we're going to list all the possible outcomes and their probabilities. All right, so here we have a 4-card hand that is dealt from a standard deck of cards. Show the probability distribution for the number of face cards in the hand. So the number of successful outcomes is 12, okay? And the number of cards available is 52, all right? And the number of trials we're going to take, or get, is 4, right? Because we're getting a 4-card hand. So the number of face cards we can get when we're dealt a 4-card hand is obviously going to be 0 to 4, right? We can have 0 face cards, 1, 2, 3, or 4, right? Those are our values for x, for the random variable. We plug the numbers into the formula. 12 choose 0 times 40 choose 4 over 52 choose 4. That's around 0.338. I'm going to round to 3 decimal places to try to be a bit more accurate. 12 choose 1 times 40 choose 3 over 52 choose 4. That's about 0.438. 12 choose 2 times 40 choose 2 all over 52 choose 4. That's around 0.190. 12 choose 3 times 40 choose 1 over 52 choose 4. That's around 0.033. And lastly, the probability of getting 4 face cards is 12 choose 4 times 40 choose 0 all over 52 choose 4, which is around 0.002. Okay, so there's a probability distribution. We can get x times the probability of x and add them all up to verify that our expected value formula actually works. Okay, so I'm going to multiply x times the probability of x. 0 times 0.338 is 0, obviously. 1 times 0.438 is 0.438. 2 times 0.19 is 0.38. 3 times 0.033 is 0.099. And 4 times 0.002 is 0.008. Okay. What is the sum of the probabilities? Why is that the case? Now you can take a second and add up the probabilities yourself. It should equal 1, right? The probability distribution, remember, is the sum of all, represents all possible outcomes. So the sum of all the probabilities should equal 1. All right, because when you're dealt a 4-card hand, you're either going to get 0 face cards, 1 face card, 2 face cards, 3 face cards, or 4 face cards. Okay, now the expected value, if we use the formula, r times a over n, that's 4 times 12 over 52, right? Which is around 0.923. Now, if we added up all the numbers from x times the probability of x from the previous slide, we should get approximately 0.93. Okay, so we're off by a little bit here. This is just a rounding error. Okay, so they should be basically the same number. All right, so we have just verified that we can just use the formula r times a over n, or we can get x times p of x and add them all up. Sorry, not x times p of x. X times the probability of x and add them all up. That's our that's our original formula. Okay, the simplified form for the hypergeometric distribution is r times a over n, and they both work. Okay, again, what does this mean? On average, if you're dealt a 4-card hand, if you're being dealt a hand over and over again, like this, you're going to average about 0.92 or 0.93 face cards. Okay, let's look at another example here. During one summer, 500 deer in a provincial park were caught and tagged. Later in the summer, 60 deer were caught, and to estimate the size of the population, and 42 of them were tagged. estimate the size of the population. Okay, now before we continue, this is just a little bit of trivia. This is basically how they estimate the populations of animals in large parks. Now they can't count all of them, so what they do is just tag a sample of them, and then they catch another sample and see how many are tagged. And the proportion that are tagged would likely mean that the proportion of total population would be tagged. Okay, so here, okay, so through these trials, we got an expected value of 42, right? That's like the expected value here. Okay, we averaged 42. Now R is the number of trials. Okay, we tried catching 60 deer. The number of possible successes available is 500. Okay, of all the deer in the park, 500 of them are tagged. So we just have to solve for n, right? That's what we're trying to solve for here. So it's just the expected value formula, but rearranged. 42 equals 60 times 500 all over n, right? If you were to simplify that, n equals 60 times 500 over 42, which is around 714. So this means there are around 714 deer at the park, right? And we don't really have to use this formula. You kind of just think about it in terms of ratios, right? Like if I did a sample, there's another way of looking at it. 42 out of 60 deer are tagged. So what number of the total, sorry, so let me rewrite that. So 500 over how much of the total is tagged, right? It's like a ratio here. Okay. So that's pretty much concludes this lesson for today. Here are a couple of practice questions. Give them a try, finish them before the end of the period, and complete the assigned textbook questions. And that's it for today.